So the next topic is automatic differentiation. If you recall, we already did automatic differentiation in MATLAB using DL array, right? And this is automatic differentiation using Pytorch. And you will notice that most deep learning frameworks, software frameworks, will have some facility to do automatic differentiation because all of these algorithms depend so critically on good gradient information, good derivative information to actually do optimization. So they've all implemented automatic differentiation, and doing automatic differentiation for neural networks, like I think I mentioned in one of the videos, was one of the major advancements in making neural networks work better. And this advancement was in the mid 1980s, I guess. Okay, so we've already looked at this video, and let's just click through this tutorial. So you should read through this tutorial, the text associated with this tutorial. I'm just going to quickly walk through Google Colab version of it. You can also download the notebook as we discussed. Okay. So this first line is just to make sure that plots are in line in the Google Colab notebook. So let me run that. Nothing happens. Actually, before we run it, let me copy the notebook to the local drive, actually Google Drive. It's creating a copy. Open a new tab. And let me actually close this. And this is now a copy of AutoGrad tutorial that resides on my Google Drive. Okay. So in principle, I could share it with you all, or if you have a Google ID, or you can share it with your friends. So recall that tensor is just an ND array, an n-dimensional array, except with some additional facility for doing GPU processing. Okay, we are going to import Torch, which implements tensors in Pytorch. Here we are just defining X to be a matrix of ones, a 2 by 2 matrix of ones. And then in addition, we are putting in this additional input to X called requires underscore grad equals true. This is actually similar to saying X equals DL array something. Let me do this here. Oops. I missed an additional parentheses there. But in MATLAB, when we did DL array once 2, 2, it created this 2, 2 matrix, which is not a regular matrix, but a DL array matrix. What this tells MATLAB is just that this is a variable with respect to which we would like future functions to be differentiated, potentially. We would like the derivatives of other functions with respect to variable. That's what we are saying, telling MATLAB here, or at least getting MATLAB prepared for keeping track of derivatives. Okay. Similarly, when we define X equals torch dot once requires grad equals true, we are defining X so that we are telling Pytorch or Python that future functions may be differentiated with respect to X. It's not that we are differentiating X with respect to something else, but rather we are differentiating other functions that depend on X with respect to X. Okay. So here's a function that depends on X. Y equals X plus 2. Let me run that. Actually, let's run this first because we haven't run this. So that's why we got an error here. So it just says tensor 1, 1, 1, 1 requires grad equals true. Then we can run this. Tensor 3, 3, 3, 3 because it's X plus 2. And then it has this additional attribute, if you will, called grad function add backward. Okay. what this means, roughly speaking, is that the thing that gave the function that gave rise to y was an addition, essentially. So the most recent function that gave rise to y was an addition. That's all, right? So it's keeping track of what functions gave rise to new variables, kind of, right? If we said, let's say, let me do z equals y divided by 2 or something, and then say print z. Okay. For y, it said add backward. For z, it says divide backward. Okay. Because the most recent function that gave rise to z was a divide. But Python will keep track of the sequence of operations that need to be gone through to go from x to y to z. Okay, so it's sort of keeping track of all those things so that we can eventually back propagate the derivatives, right? So we can differentiate z with respect to y and then y with respect to x, and then sort of use chain rule essentially to compute the derivative of z with respect to x, and that's called back propagation. But right now, all Pytorch is doing is sort of keeping track of the dependencies by sort of appending this additional variable that keeps track of what functions just happened. We don't necessarily have to pay attention to what these things are. It's just an internal thing. We don't really have to look at it, but it's there, okay? We won't actually be explicitly, well, here they're actually calling it, but it's not like incredibly insightful. It just says, okay, some object, this weird number is the memory location on the computer of that object. Okay, so not that useful, I suppose, at least for most of our purposes. Okay, here we in fact have another z that variable that they've defined. Z equals y times 3. If we do that, and then we go print z and print out. Basically, z is multiplication because that's the thing that happened most recently, and out, which is basically mean. Z is a matrix, 27, 27, 27, 27, a 2 by 2 matrix, and then out is basically the mean of all those numbers. And if you say print out, what you get is a single number, 27, because that's the mean of all these 27s. And it says the grad function, most recent function that gave rise to the out variable is mean, essentially. Okay. Okay. So let's run this. So this is now a more complicated function, I suppose. Well, A is a 2 by 2 matrix of normally distributed random numbers, and then you replace A with this more complicated expression, A times 3 divided by A minus 1 something. And then they say print A dot requires grad. Let's see what that gives us. When they say print A dot requires grad, it says false. In other words, we are not keeping track of derivatives with respect to A, right? Because A, we haven't, it's not a function of X, and it's not something that we explicitly called out as required grad equals true, okay? But then we can now flip a switch and say A dot requires grad underscore true, and then print A dot requires grad, and then it becomes true. Okay, so now for future variables that depend on A, the variable A, it will now have this grad function. Okay, so if we say print B, it's a tensor with value 118.8014, and then grad underscore function is sum backwards. There's a sum here, I guess. Okay, that's the most recent function that gave rise to B. I think secretly it keeps track of everything that gave rise to B from the initial variables, but what it displays is just the most recent variable. Okay, so now all we have told um, Python or Pytorch is to keep track of the dependencies of the variables to be prepared for automatic differentiation of some output with respect to some input. Okay, the differentiation has not actually been done yet. Um, to actually do the differentiation, you have to go backward in the chain of dependencies and differentiate, say, in this case, out with respect to x. Okay, so we started with x, x became y, y became z, z became out, and then we can propagate the chain of partial derivatives backward, and that is done by doing this out dot backward empty brackets. It is important to have those empty brackets, it turns out, and they call it back propagation, but propagating chain derivatives, chain rule, automatic differentiation, these are just other words for the same process. Okay. I ran this thing and it did the propagation of chain derivative chain rules for the partial derivatives. It's fine, and then we can now print the actual partial derivative matrix. Let's run this. Okay, so this is x dot grad. What does this mean? What does x dot grad mean? X dot grad actually means the derivative of the output variable, because what we did was out dot backward. This variable out, the derivative of this variable out with respect to x. This is a scalar, out is a scalar, it's a single number, and we are differentiating that single number with respect to a 2 by 2 matrix, and the derivatives with respect to that 2 by 2 matrix is represented as a 2 by 2 matrix, a tensor as well, and these are the 4 derivatives. It so happens that they're all equal. Doesn't matter, but that's the derivative. So we want to be very clear here. X dot grad is not the derivative of x, but it's the derivative of output with respect to x. So you can really do only x dot grad with respect to one output variable at a time. You cannot do multiple things, at least in this framework. We can do it one output variable at a time, where you define what variable you want to differentiate with respect to, and then go x dot grad, and you print that. Okay. So if you wanted, for instance, the output with respect to of z with respect to x, let's do that. For some reason, my computer has slowed down, but let's plow ahead anyway. Backward. Maybe I should close my MATLAB. Let me close my MATLAB. By the way, doing this out dot backward is similar to how you guys used DL gradient inside functions for automatic differentiation. So let me just close MATLAB. So when you run DL gradient in MATLAB inside a function, it actually, I think, does this back propagation. Okay. Z dot backward, do that, and then print x dot grad. Okay, so let's actually run this thing. So z is a function of x, or let's say y. Y is a function of x. What was the one that was before? Okay, for some reason my computer is rather slow. Okay, z is y times 3, and out is z dot mean. Okay, so it's going to give us an error now, but it's fine. So z is a 2 by 2 matrix, I believe, and but we are differentiating the 2 by 2 matrix with respect to another 2 by 2 matrix X, and hoping that x dot grad gives you the derivative of z with respect to x. Okay, you see the thing turn to red, and it says error blah blah blah. Grad can be implicitly created only for scalar outputs. Okay, z is a matrix or tensor output, and they would like us to use this grad function only for scalar outputs. This out thing was already a scalar function. Out was a mean of all the z elements, and so it allowed us to take the gradient, but it doesn't allow us to take the gradient of z with respect to x. Okay, it's not that these partial derivatives are not defined. You can imagine a tensor of some sort or higher dimensional matrix of some sort that gives you the derivative of the elements of z with respect to the elements of x, all possible combinations. But it's just that the framework doesn't allow us to do it directly, at least. They have some additional information about what kinds of things you can get if you are differentiating something with respect to z, or something that is more like a matrix. I'm going to skip that because that's not super important for our immediate purposes. So, but what I'm going to do is define another x, y, z, z dot. We've already done mean, maybe standard deviation. Okay, so z equals z dot standard deviation. Now it's going to be the standard deviation of z. Hopefully that's a single number, and then we can do z backward, and then we can do x grad. So let's try that. Interesting. Z dot std doesn't have. Let's actually print z and see what happens there. And let's put this as a comment. Computer is slow to a crawl for some reason. Not sure why that is so. Okay, looks like it doesn't like standard deviation. Let's actually see. Let's fix this now. Let's just print z, and then I will do some operation that produces a scalar. Maybe we've changed z to something. Aha, z is some weird thing here. I think we've unfortunately overwritten z. Okay, built-in method of tensor object. Okay, I see. Now I think what I see what the error is. So let's actually go z equals, I don't know, x times x, print z. So that's z. And then let's go z dot std and then open and close brackets. That's important, it turns out. Maybe let's call that p something. And we can do print p. Okay, so P now is the standard deviation of Z. And what I think I forgot to do last time is actually have this open close brackets. So if you leave out the open close brackets, it actually assigns to P the actual method of computing the standard deviation as opposed to the standard deviation. So it's weird. So that's why it was complaining. And now I think we now have P equals basically zero because the standard deviation of four numbers is zero. And it says the sort of most recent function that gave rise to P is the standard deviation. Okay, so all good. Now we can go P dot backward. And then it's important to have this open close brackets because I think if you do not have that, it just we are referring to the method rather than executing the method, I suppose. Okay. Now we can do P dot backward and then go X dot grad. Run everything. Okay. So X dot grad is 4.5, 4.5, 4.5, 4.5. That's the derivative of P with respect to X. Okay.